Sir,
Yes, please.
so in the Fe3 phase diagram,
Yes.
the A2 line is between gamma and gamma plus alpha, and the eutectoid line is the A1 line.
Now A3 line, A1 line, and ACM line. These three lines I mentioned.
Yes, the A1, A3, ACM. The A2 line was between which?
You don't have to worry about it for the time being.
Okay, so it was in the phase diagram. I saw that thing. That's why.
I didn't mention even what does it mean AC1, ER1. Those will be taught next semester when you take heat treatment and phase transformation courses. Okay.
And so, what is the
I
why?
hope that phase diagram which I showed you. Just give me a second.
Okay, sir.
A2 line, do not worry. Eutectoid line is A1. Okay, eutectoid horizontal is A1. Then gamma phase boundary, one left side is the A3 curve, right side is ACM curve. A2, do not pay attention to it. Okay?
Okay, sir. And one another thing, what is the reason between the formation of coarse and fine pearlite? Like because of the temperature difference, what is happening?
Cooling rate. You see, everything depends on the nucleation from austenite to pearlite. So if you go to the TTT diagram in the higher temperature, the delta G is negative, delta G negative is less compared to delta G negative for pearlite formation at lower temperature, relatively lower temperature. So nucleation of the pearlitic region, and pearlite, how does it nucleate? Cementite nucleus, then alpha ferrite and cementite, alpha ferrite this way. So nucleation rate and the number of sites will be small for relatively higher temperature compared to relatively lower temperature. So the eutectic region size, each eutectic region size will be smaller in case of high undercooling, meaning relatively lower temperature, and it will be larger in case of less undercooling at relatively high temperature. So that's the reason it's called fine pearlitic structure, coarse pearlitic structure. Fine means higher amount of undercooling, smaller regions size of eutectoid pearlite. That's found by eutectoid reaction.
And so another thing, can you again discuss about the angle of 55 degree in the lower Benite transformation?
Hmm. I didn't follow the question.
So in the lower Benedict transformation, when the lower Benite is formed, the cementite is sorry, not cementite. I guess that Fe2.4C is
Ah,
precipitated at an angle of 24, sorry, 55 degree. Now,
with respect to the axis,
ferric
axis means
axis of the ferric.
across the length direction of ferrite needle. Ferrite needle, that axis along its length. Or if you draw an imaginary line, so it makes 55 degree to it. Do you follow what I'm saying?
Yes.
You make a ferrite needle, extended V shape. Draw a line along its central axis and make 55 degree with respect to that axis where epsilon carbide precipitates. You go to that video, I drew it.
Okay, sir. But like, there's not much time. Okay. And so for benite is the both Fe3C and Fe2. Both carbide and epsilon carbide both have the same phase, like, right?
No, so different structure,
Sorry.
different crystal structure. Fe2.4C and Fe3C are not having same crystal structure.
No, sir, not the same crystal structure. I was telling that, but that what both for both the transformation from Fe, it is we can find benite.
In upper benite, alpha ferrite nucleus first, then Fe3C, and so on. Just opposite to pearlite. In lower benite, alpha ferrite nucleus first, and then epsilon carbide. Epsilon carbide is Fe2.4C. And that's much you should know, not more than that now, because benetic transformation is a very controversial subject. A lot of discrepancies are there, a lot of arguments are there.
Okay, sir, got it, sir.
Hmm.
So once
Oh,
again, please.
yes, another thing. I had another doubt, sir.
Sure, ask as many as you wish.
Yes, once you told right that when there is a fast rate of cooling, the solidus and solvus curves they shift to the left. If I take for the alpha solvus and alpha solidus.
Hmm.
So what is that phenomenon called, sir?
No, that phenomena is because if you cool faster, alpha a liquidus, alpha solidus shifts towards the left, means you do not give sufficient time for the first solid to nucleate to second solid composition change. That is not happening. You follow? You just see that along the liquidus, you mark temperature T1, T2, T3, T4, and so on. The first solid is forming at T1 temperature. So it has a composition. And T2, composition will change. It will get rid of B in A and so on. So you have to give sufficient time for the diffusion to take place. If diffusion is not taking place, the composition change from S1 to S2, solid 1 to solid 2, will not be complete. So it will be somewhere between composition of solid 1 and solid 2. Hence, if you draw the line, solidus line, it will appear like it is shifting towards the left. It doesn't have any terminology. It is for non-equilibrium cooling, the second solid, third solid, fourth solid, and so on, forming out of liquid, will not have the equilibrium composition, rather lesser amount. So for that reason, the solidus curve moves towards the left. Gauri had a question.
Yes, sir. Is Rian's doubt completed?
It's okay for now.
Rian,
Yeah.
you understood what I said?
Yes,
And
sir.
that results in a phenomena called coring. Coring means the solid form, but it has a gradient in composition from the core to its surface.
So, what is the relation between the radius of the nucleation which is forming and the temperature, the undercooling temperature, undercooled?
The equation I gave you.
Um,
Check that.
which one, sir?
This
I,
radius, critical nucleus radius, R star, that
yes, sir.
derivation I gave. Check the video, that derivation I gave, both for R star and delta G star for homogeneous nucleation. And energetics of heterogeneous nucleation I gave as a function of homogeneous nucleation. And I said you derive
So,
that.
so you're telling about the equation of the delta G. There's something with delta G, right?
Delta G star and R star.
Equal,
Yes, sir. Yes, I remembered it.
Is it the same, sir? Like we can apply that over here, right?
Yes.
Understood, sir.
I gave you for homogeneous nucleation, but you will have a further modified form for the heterogeneous nucleation, but
We derived
essentially
it.
same.
We derived it, sir.
Yes.
Sir, can once please check the chat. I have pasted the screenshot of the uh, particular question what I was reading yesterday. Here they have said that for a 40%, 48 percentage tin and 68 percentage of PB alloy at 150 degrees Celsius, what phases is are present? So when we plot those things, like when we just analyze from the graph, we can see that it's an alpha plus beta region, and after that they have. This is Vile, sir. I forgot
Huh?
the author. Vile.
Relay means
Vile, just a second, sir. It's of Callister.
Callister book
Callister.
in the soil which is not acting as either solid nor solvent.
Huh. Like we
No,
can interpret this thing,
I
right?
cannot,
Some.
I cannot magnify that writing. Okay. For 48% tin, 60% lead alloy, what phases are present? What is the composition of the phases? Look at this temperature composition phase diagram. Inside is the alphabet, both alphabet.
Okay.
Because two phases are present, it becomes necessary to construct a tie line across the alpha beta phase field at 150 degrees. The composition of the alpha phase corresponds to the tie line interacting with alpha alpha phase boundary about 11% in it and denoted as C0. This is similar for the beta phase, which has a composition approximately 98% in and 2% A. This is fine, but there is nowhere they written that it is existing as a pure element.
Yeah, sir. Like you can see that in the alpha thing, plumbum is 89%, and in the beta thing, plumbum is 2%. That means the combined is 91%. That remaining 9% of plumbum is like neither in alpha, neither in beta.
8% in.
Actually, they have given the formulas of how to calculate it.
Let me read that thing. 1 minute.
Yeah.
That's no problem. Did they tell you what is the volume fraction of each? You did it. The total number of tin and lead atoms will not change from the system. But relative, these are the composition of each phases. And when you have the fraction of each phases from the phase diagram, you will get the total amount of each of those lead and tin elements, which will be 100% for each.
So the question still remains the same, right? The 89 percentage plumbum is in alpha, 2% is in beta. That means some more 9 percentage of
Draw
plumbum
that
metal.
phase diagram, you will figure it out. Draw the phase diagram, point those things. Those are the compositions of the two phases. And if you have the tie line, then it will show the relative fraction of those two phases. These are the composition of the two phases.
Okay.
But relative fraction will change. That will give you the total number of lead and tin atoms will be unchanged. But these are the composition of alpha and beta. If you add them together, any phase composition from any phase diagram, it will not be 100 that way, the way you are showing.
Okay.
Do you follow me?
Understood, sir.
Okay, sure.
Slightly there is a confusion, sir.
Think about it.
Yeah, I will.
What happened to all of you? I can't see you there. I got
So we are
minimum. Huh? All got minimized. I don't know. Response of require. Wait a minute.
So I guess you pinned your
I don't know, when I try to close your expanded window, something funny happened. Just wait for me a minute. Okay, Gauri, still you have doubts?
Sir, he just texted me his network is gone a little bit.
Okay.
I came back.
Uh,
That's it, sir.
Try to do it on a phase diagram. It will be clear to you.
Yes, sir.
Next question.
so
Hmm.
I was observing something like in the TTT diagram. If we
Uh-huh.
go above in the temperature, the PS and PF, the difference between PS and PF is shortening. So, is there any time temperature or for a very long elongation time when they actually submerge? Can it happen ever?
Say it again once again. I did not follow it.
So for the TTT diagram, as we
Uh-huh.
go as we go above in the temperature, we can see that the PS and PF difference is becoming less and less, and as we give more time,
Perlite formation is a diffusion control process. Okay.
yes, sir.
So below 727, perlite will form from austenite. Higher is the temperature, higher will be the rate of diffusion. So perlite starts forming. Will from there, once the perlite starts nucleating, means Fe3C alpha ferrite, it will continue very fast because of the high temperature.
Okay. So it's the kinet. So it is a kinetic system rather than the thermodynamics.
Yes. Yes.
Okay, sir.
It is combination because you have a driving force.
Yeah.
Also, thermal energy kinetics plays a major role in it. You are right.
Okay, sir.
Sir,
Ah,
sir, in the conversion of austenite to martensite, sir, there are like 12 edges which has equal probability of carbon atom. So, sir, why the like I didn't get why shear only happens across the axis?
when you drastically quench a sample from austenitic state to the say oil or water in room temperature, there is a huge amount of thermal shock take place. So any stress develops, it has a two components, a shear component and a what component?
Sir,
First year mechanics.
sir, stress, volumetric.
Stress is there, but a force if you apply a load, one
Sir,
shear
tension compression.
component, normal to the slip plane. The shear stress applied along the vertical axis, it tries to contract it, but there is a carbon atom in one of the edge centers along the x-axis, along the vertical axis of a unit cell out of say approximately 500 unit cell. You can compress to by a 20% or so if you have a carbon atom there. But along those two basal axes, A1 and A2, 12% expansion takes place. And C by A ratio is greater than unity if carbon composition of the steel is greater than 0.2% or higher. 0.2% or less or pure iron, it becomes 1. But this transformation is not by the diffusion of carbon atoms in iron. It is by the shear stress applied along the vertical axis, along the C-axis. That's the reason martensitic transformation is called diffusionless shear transformation.
Sir, my question is why the stress applied on C-axis? It can also be applied across A-axis, no?
Is applied, that's the reason it expands by 12%.
Okay, sir. Okay, got it. Okay.
Okay. Any other question?
Hello, sir.
Yes, name please.
Gaurav Patel.
Okay, Gaurav, please.
Yes, sir. So you told that different alloying components have an effect on the martensite start and martensite finish temperature.
I gave an empirical relationship.
Yes, sir. So is there any difference between the effect on the martensite start and martensite finish temperature? Like it
Well,
affects more the start.
is more or less similar.
Okay, sir. So,
Okay.
so is there any reason for that similar effect?
It will be similar because the alloying elements lower the MS and MF temperature. This is not a theory, it is empirically derived expression. It's not an equation. So they find you, they have some data points, they plotted it, and so you get this kind of thing.
Okay, sir. No theory. Okay, sir.
Okay.
Yes, sir.
Got it?
Yes, sir. Empirical relation. What to do about it?
Yes, empirical. Hall equation is also an empirical relationship.
Okay.
Any other question?
Hello, sir.
Name please.
Sir Rishabh.
Yes, Rishabh.
So I have a doubt in the divorced microstructure that you taught on 28th. Can
Yeah.
you show the slides of that day?
I don't have the slides with me right now, but I can tell that if it is a composition which is not cutting the eutectic horizontal, but lesser than
Yes,
that,
sir, not that. Sir, when we cool it down further, it again cuts the alpha plus beta curve. So will there be any change when it cuts it again?
no, it doesn't cut alpha beta curve. It shifts towards the left.
No, sir.
That
So below the eutectic temperature, it again intersects the alpha plus
does
beta
not
curve.
intersect twice. The solidus curves moves towards the left.
So I'm
Solidus
saying below eutectic temperature. So like along that vertical line, it will intersect.
entire solidus curve moves towards the left. So it doesn't cut the solidus curve until it goes down to that temperature. And because of the shifting of the solidus curve towards the left, the eutectic horizontal gets shifted towards the left. Under equilibrium, this composition will not cut the eutectic horizontal. However, due to the shift of the solidus curve towards the left, eutectic horizontal gets shifted or extended towards the left. Hence, when the liquid reaches the eutectic temperature, for the eutectic composition, a small amount of eutectic solid alpha and beta forms. So primary alpha should have been the microstructure, but because of faster cooling, eutectic alpha and beta forms, and eutectic alpha preferentially nucleates over the primary alpha. So it looks like alpha and small globules of eutectic beta formed. Hence, this microstructure is called divorced eutectic structure.
Hello, sir.
Yes.
So does the greater amount of supercooling also resemble the faster cooling? Is that so?
Anyway, if you cool it other than the normal equilibrium slow cooling, it is fast cooling. Always fast cooling, other than equilibrium cooling. You cannot cool slower than the equilibrium cooling.
Yes.
And how fast it is depends upon the cooling rate. Any question? Anybody has any question? Are you there?
Yes, sir.
Yes, sir.
Anybody has any more question?
I think no, sir.
Think about it, then I'll close it. I'll start Viva at 5 minutes to 10. Argodip? Argodip, are you there?
Yes, sir.
Should I leave or you will join it and set it up?
Sir, the meeting for the Viva already has been set at 10 a.m. So that is a new meeting. You can leave
Okay,
this
so I'll
meeting
leave
and
this. So I shall leave this meeting, right?
yes, sir. Yes.
Okay. Okay, guys, please tell me if you have any more questions. I'm all there for you.
So I'm sharing a screenshot in the chat.
Okay. What?
So at T5, temperature T5, below that, it again cuts the.
Wait a minute, I again lost things. Just 1 minute. Oh, कहाँ गया मैं? When I expand and cannot come back, I don't know what is going on.
Hello, sir.
Huh.
So there was a topic including some stages of tempering, I think.
There are 4 stages of tempering, and 5th stage is your secondary hardening.
Yes, sir. So, if you have time, if you could just explain that once again, sir. I couldn't understand completely in that lab lecture or anywhere else.
No, I explained that thing in details in the theory. My class. Please refer to that video because it will take a long time. There are 4 stages and overlap temperature regions. Okay. So I need those slides to explain it. It will take almost a period. So if you have any specific question about tempering, I'll be more than happy to explain. Otherwise, if you want me to repeat the entire thing, I request you to go through that class video, please.
Okay, sir.
Okay.
I'll go through.
Okay, that will be great.
Thanks.
Thank you. Any other question?
So could you see the screenshot I shared in chat?
I can see that thing. Tell me.
Yes, sir. So like when we cool it at a faster rate, so you said the alpha solidus curve gets shifted to the left, so
Yeah.
at the eutectic temperature we get some amount of eutectic microstructure also. So when we further cool it down at T5, it again intersects the alpha plus beta solidus curve.
Beta
So
precipitate forms.
okay, sir. So
Beta
means
precipitate.
it's a dendritic structure and beta is in between those dendrites. So
Beta
where will the
precipitate forms. And preferentially at the grain boundaries or interdendritic boundaries.
so it's more or less the same structure, right?
No,
So
globules of beta eutectic forms. Globules, spheroids, same. Big. Precipitates will be very fine. You perhaps will not be able to resolve it with optical microscope. You may need to see the sample in electron microscopes. So that is
so
beta.
so what is the difference between the beta that was already present when we cut the eutectic temperature and when it reaches T5?
That is the eutectic beta.
Okay, so
And beta precipitates.
so earlier it was present between the dendritic arms. So
No,
and
no, no.
the
The eutectic, look, alpha dendrites formed due to
yes,
coring.
sir.
Eutectic alpha, eutectic beta forms. Eutectic alpha forms on the primary alpha dendritic shape in this case, on it preferentially nucleate. In between these alpha dendrites, eutectic beta globular or spheroidal shape forms. And below, cooling below the alpha solvus, excess B atoms come out and forms B rich precipitate, beta precipitate. It forms on the grain boundaries or the boundaries between dendrites.
Okay, so the grain boundaries of this divorced microstructure, right?
For the entire sample,
Okay, sir.
wherever they see a boundary, preferential site to nucleate.
Okay, so so actually the grain boundaries are not means it is not in this picture, so I got confused.
It can vary. Here is show dendrite. Dendrite is also a single grain. We can call the dendrite a grain, but generally call it dendrite and interdendritic region, boundary between two dendrite nucleates.
Okay, sir.
Okay, each dendrite is a grain.
Yes, sir. Thank you,
Each
sir.
dendrite is a single grain. Okay,
Yes, sir. It's clear.
very good. So, best of luck to all of you. So I shall leave and rejoin 5 minutes to 10 for Viva. Okay, dokie?
Yes, sir.
Yes, sir. Thank you.
Okay. And if you have any other question before Vivas, please don't worry to call me up. I'll explain again.